I have one
This
doubt.
meeting is being recorded.
Any question?
Yes, sir.
Uh,
Yesterday, in one expression, we have used n into p is equal to ni square.
uh,
So, how this relation goes for a extrinsic semiconductor?
मैंने
Means
बोला
in
कि ये जो लॉ है that is valid for extension semiconductor also. Okay, that is valid for intrinsic as well as for external semiconductor. Okay, only the difference is
so,
the internal semiconductor your Ni is equal to Pi. The number of electrons are equal to number of holes. When you go to extrinsic, okay, the majority charge carriers are electron. The number is very high compared to number of majority charge carriers are very high compared to number of your minority charge carriers. In N type you have a electrons high concentration of electron, and your P type you have a high concentration of holes. Okay.
okay, sir. So, in extrinsic semiconductor, ni square means that semiconductor when it is intrinsic at that time of carrier
They will
concentration, is
give
it?
question, they will give you that when is the what is the intrinsic care concentration of that host material. Okay, the per goes always equal to Ni square. Okay, so if number of electrons increases, number of hole decreases. So we have done yesterday question also, na? Okay, from that questions also you can see numerical problem that number of your ND, okay, is very high. Yesterday we have done a question. Okay, let me give you the numbers that questions where we have calculated the concentration was given. Okay, so yesterday we have done that p type of semiconductor. Okay, where we have been given the concentration equals to 1.1 to 10 to the power 20. So total of atom was 4.5 into 10 to the power 28 order. Okay, this was the order of impurity atoms. Okay, so when we have done we solve this one, this was 4.4. Okay, this one, give me 1 minute. So Na concentration was given 4.4 into 10 raised to power 28. Okay, and total number atom, and they told that each one atom is replaced by this much of atom. So from here we got the concentration of impurity atom equals to 1.1 into 10 raised to power 20. Okay, per meter cube. Now this concentration is very high. Okay, when you calculate for intrinsic carrier concentration. Okay, like now Ni also given. Ni was given you 2.4, 2.4 into 10 raised to power 19. Okay, and from there we have calculated the number of holes. So you see this is a one order higher than this concentration. Okay, so the multiplication is 38. So out of 38, 20 power is electron, and remaining 1 power less than this one. These are holes. So product always remains same, but the electron becomes high, and your this holes become down. Okay, in P type is become opposite, holes become more, and your electron becomes down and lesser. Okay, so this is a particular numerical, and actually this number is lower than this one. Okay, if you calculate for silicon, this number is only 10 raised to power 10 only per centimeter cube. Okay, so this number is actually very low, but multiplication of this number is very high. So when I calculate intrinsic like silicon 10 raised to power 10, so total becomes 10 raised to power 20. Okay, so this is very high, very close to this multiplication. Okay, but the number of this electrons or holes, okay, they got down, but the multiplication will remain always same. Okay, I will discuss this thing one time more. Okay, let me discuss in detail tomorrow. Okay, I will come some good example, the practical values, then you will understand. Okay, so
Okay.
now let me start today the Fermi level position. Okay, so we have already done the position of intrinsic semiconductor. Now let me solve for our position of Fermi level. position of Fermi level in n-type semiconductor. Now, if I talk about n-type of semiconductor, I know what is concentration of electron is given by Nc exponential minus what Ec minus Ef upon kBt. Okay, this is the concentration of electron in conduction band. Now we have already calculated the approximate concentration of electron in conduction band, that is equals to your mobility. Okay, sorry, impurity.
सर स्क्रीन में उस सेट का दिखाई दे दे रहा है.
Yes, I'm making 1 minute. So position of, now from here you can find, if I put n equals to nd, that will give me the position of Fermi level in n-type material. Now just you can rearrange and you can get the position of Fermi level. Okay, so if I send this there, it will become exponential. Okay, Ec minus EFN upon kBt. Okay, and this will become Nc upon Nc is generally higher than Nd. State is always more than the carriers, so Nc is higher Nd. So from here you can get Ec.
सर
हाँ
सर ऑडियो
सर
प्रॉब्लम हो
यहाँ
रही है.
सर यहाँ EFN जो लिखा है
हाँ,
वो EFN का मतलब N टाइप सेमीकंडक्टर है ना?
yes, N-type semiconductor.
ओके सर.
Am I audible now?
यस सर.
हाँ, so ये N-type semiconductor के लिए जैसे ही मैंने everything depends on concentration ना. I told you this gap will decide concentration. Okay, if the gap is given, we can find the concentration. If the concentration is known, we can find this gap, this difference we can find. Okay, and at any temperature. So this is now become Fermi level of n-type material. Once you put this here, if you put this is equal to Ni, this become Fermi level of intrinsic semiconductor. Clear? Okay, so this is general expression. Once you know this value, okay, you can find the Fermi level position of any semiconductor. So this become now E. This is not EFIN. This is EFN. Okay, EFN. Okay, so EFN, ES minus EFN. This become KBT ln NC upon ND. Okay. Now if I want the position of Fermi level in n-type semiconductor, that will become EC minus KBT ln NC upon ND. Okay. Now if I have an n-type of semiconductor, okay, if this is my conduction band edge, okay, conduction band, and this is my valence band, so somewhere here close to the Fermi level or close to the conduction band, I will be having the position of Fermi level. Okay, we can put this value, theoretical values. Okay, kBt is always very low, 25 millielectron volt in your value. Is kBt is very low, okay, at room temperature. And if you put these values, so this value is very less compared to this band gap. So my Fermi level always comes close to the conduction band edge. Okay, so in n-type your Fermi level is close to the conduction band, and in p-type your Fermi level is close to the valence band. So this is the position of Fermi level, okay, in n-type semiconductor. Okay, now we can write this concentration, okay, this position in terms of intrinsic Fermi level also, because we know when is intrinsic semiconductor, then their position is somewhere here, okay, somewhere middle. So I can modify this formula also. So this is one formula. Okay, now let it be modify this formula for another formula. You can use any formula depending on the values given in the question. Okay, now any voice problem, any audio problem?
यस सर, बैकग्राउंड से खिड़खिड़ की आवाज आ
हाँ
रही है
सर,
कुछ.
बैकग्राउंड में नॉइस आ रहा है.
बैकग्राउंड में क्या नॉइस?
But okay, sir. We can
I don't.
adjust.
Yeah. Okay. Please. I'm not able to find what is the problem. Okay. So now this is my what? This is my ND. Similarly, if I want to write NI, carrier concentration, NI. Okay. So NI also can be written with this formula. Okay. If it is the anti, if it is an internal semiconductor, so instead of if I write this NI, I can write what? This is also NC. Same exponential. Okay. What I can do now? I can write minus ES. Okay. Instead of now, I can write the EFI, EFI, the Fermi level of intrinsic material. Okay, KBT. Okay. Now, what I can do, I can use this expression to calculate your concentration again. Okay, so I can find a ratio. I can find the ratio of ND by NI. If I find the ratio of ND by NI, what will give me? It will give me exponential minus ES minus EFN by KBT upon exponential minus ES minus EFI upon KBT. Okay. Now from here also I can find the position of Fermi level. उसमें आपका EFI भी आ जाएगा. EFI से कितना दूर है, above है कि नीचे है. Okay. So depending on the difference, if they have given the difference of Fermi level of those Fermi level, then also you can find. Okay. So from here what I can do, just solve this one. Okay. So if I solve this one, what will come? I want this EFN, this become positive. So this EF positive, ES minus. If you go above, okay, then what will become? ES positive and EFI negative. Okay. So I can write ND.
Minus EFI minus EFN.
Okay. Exponential. I can send a ln here. Okay. I can write keep sorry, ND upon NI, okay, equals to exponential. Okay. Then I have minus EC plus EFN, okay, upon KBT. And if I put this value also, it will come now plus EC, okay, and plus EC and minus EFI. So now EC is we are EC removing. Okay, EC removing because generally you don't know the conduction band age. So now in this formula we don't have a EC, so EC can be cancelled. Okay, so I have that EFN minus EFI is equals to KBT ln ND upon NI. Okay, now I can write my EFN is equals to EFI, okay, plus KBT ln ND upon NI. Okay, so this is the second formula for position of Fermi level. Okay, so this is a useful formula.
सर केबीटी कैंसिल नहीं होगा?
क्यों कैंसिल होगा? एक्सपोनेंशियल में है ना,
भी था ना,
उसमें कैंसिल कैसे होगा?
नहीं होगा सर, सही है.
ओके, सो नाउ ये फॉर्मूला बहुत इंपॉर्टेंट है कंपेयर टू जो एज वाला फॉर्मूला है, कंडक्शन बैंड एज वाला, क्योंकि इसमें हमेशा क्वेश्चन में हमको एनआई दे रखा होता है. ओके, एंड कंसंट्रेशन भी दे रखा होता है. So इस फॉर्मूले से we can find out what is the position of Fermi level. Okay, and then you have to take know these things also. Okay, if it is an intense semiconductor, then the EFI is somewhere here. EFI is somewhere here. Okay, and if you know the band gap, EG, so you should know your EFI is just the middle of this band gap. So this structure you should know whatever the values they ask. Okay, depending on this structure you can find. Okay, this is conduction band and this is the valence band. So middle में your EFI है and somewhere here close to here, if you make this N type, your EFN is somewhere here. Okay, So if you know this distance, okay, if you know this distance, if you know this distance, okay, you can calculate this distance. Once you know this distance, okay, you can find what is the concentration, or reverse concentration is given, you can find what is the position of Fermi level. Okay, so that's that diagram you should know, okay, in order to solve the problems. So this was the position of Fermi level n type. Yes.
सर ये EFI हमेशा मिडल में ही होगा
EFI हमेशा
सर
मिडिल में होगा।
EFI वो हमेशा
EFI
मिडल में ही होगा
वो हमेशा मिडिल में होगा, वो इंटरसेक्शन सेमीकंडक्टर का है ना, वो तो इंटरसेक्शन सेमीकंडक्टर का तो हमेशा बीच में रहेगा। ओके,
ओके
now position of Fermi level for p type of semiconductor. So similarly now we can find, so this is two formula for n type. Okay, now same we can do it for p type, and we can calculate the position of Fermi level for p type. Okay, so for p type I know that my concentration of holes in valence band is equals to Na. Okay, and this is equals to what? Nv exponential minus Ef minus Eb upon kbt, isn't it? Okay, so from here also you can find the formula for EFP. This become EFP now. Okay, so find the formula. What is coming? Tell me. Position of Fermi level. Okay, so if you find this formula EFP, okay, this should come EV. Now it is above EV. Okay, EV plus KT ln NV upon NV. Check it, ये आ रहा है क्या?
Yes, sir.
Okay. So now similarly we can find the next formula. Okay, so this is the one formula. You can find next formula also in terms of Ni. Okay, so I'm erasing this one. Next formula is what? Next formula you can also write this Ni. Okay, Ni equals to, also you can give in this formula, and because Ni is also equals to number of holes. Okay, so this you can write exponential minus, okay, EF, what should I write? EFI minus EV upon KBT. Okay, so now you can bring the formula in terms of Na and Ni. Okay, so Na upon Ni equals to exponential minus EFP minus EV upon KBT. Okay, and exponential minus EFI minus EV upon KBT. Okay, now if you solve this one, okay, you can write EFP is equals to EFI, okay, minus KT ln Na upon Na upon Ni. Okay, so this is your एक फॉर्मूला. ओके, सो ये चारों फॉर्मूले हैं. ओके, यू कैन यूज अकॉर्डिंग टू द प्रॉब्लम. प्रॉब्लम में क्या दे रखा है और किससे आपका आसानी से हो रहा है, यू कैन यूज दिस फॉर्मूलास. ओके, तो ये तो हमने क्या निकाला, अभी हमने पोजीशन ऑफ फॉर्मूला निकाल लिया, हमने कंसंट्रेशन भी निकाल लिया. ओके, नाउ वी आर इन द पोजीशन टू डिस्कस कंडक्टिविटी ऑफ एक्सटेंसिव सेमीकंडक्टर. ओके, so shall I erase this one?
No, sir, just wait for 2 minutes. Yes, sir. Done.
Now, if you want conductivity of external semiconductor, so conductivity of extrinsic semiconductor. Semiconductor. Okay, I am taking the temperature range where it is constant. Okay, generally extrinsic conductivity also depends on temperature. Okay, so I'm taking mid-level temperature range. Mid-level temperature range is the range where your all the ions get ionized, all the impurities ionized. Okay, so I'm going the temperature range. Okay, so assuming the temperature range. Okay, range where all the impurity items, all the impurity, okay, donor as well as acceptor get ionized. Okay, so I am not in the range very low. I am not discussing this temperature, but very low range at frozen temperature where this impurity cannot ionized. Okay, similarly I am not going very high temperature where your semiconductor becomes again intrinsic. So I am the mid-level temperature range. Okay, so I am in mid-level temperature range. So now if I want to calculate the conductivity of n type, so conductivity of n type, conductivity of n type. Okay, so I know the number of electrons in conduction band is equals to nd, assuming complete ionization, and number of holes in n type is equals to ni square upon nd. Okay, now if I want conductivity, okay, conductivity is what? Conductivity is n e mu n plus p e mu p. Okay, now if I put this value here, this comes out nd e mu n plus pn. This is nn pn. Okay, now pn is what? Ni square upon nd e mu p. Okay, now this generally is very high compared to this one. Okay, if suppose there is a only difference of one order, okay, suppose this is a one order difference in between these things, so what become, this become your point one. Okay, if this is one, this become point one. So generally difference more than one order. So this value, okay, this value is neglected compared to this one. Okay, if you want to calculate exact, you can use this formula, but when you add this term, okay, into this first term, then this term will be negligible. Okay, so there will be no use to add this term. So I can write just my conductivity is nd e mu n. Okay, this is the formula for conductivity of n type of semiconductor. Okay, so I'm assuming it is constant in range where it is constant. Okay,
सर एक बार वो फिर से एक्सप्लेन कर दीजिए वो नेग्लिजिबल क्यों?
नेग्लिजिबल भी जैसे ये ni स्क्वायर पर nd का जो रेशियो निकालते हैं ना, वो इसके ऑर्डर से कम होता है। जैसे हमने कल क्वेश्चन किया था, उसमें क्या था हमारा क्वेश्चन, nd हमारा क्या था, nd हमारा था ऑर्डर ऑफ 10⁻20। ओके, और हमारा जो होल्स की कंसंट्रेशन आया था पीटर सेमीकंडक्टर में, हमारा Na था T20, और हमारा जो P था N था इन P टाइप सेमीकंडक्टर, इट वाज ऑर्डर ऑफ 10⁻18। ओके, सो तो ये ऑर्डर में डिफरेंस है ना, ऑर्डर में, तो इसको ऐड कैसे करोगे भी? सपोज मुझे 10⁻20 में 10⁻18 ऐड करना है, तो क्या आएगा, क्या आएगा बताओ? इसको 20 बनाओ पहले, तो 20 बनाने के लिए फिर मुझे 0.01 से मल्टीप्लाई करना पड़ेगा। Okay, now if I add this one, this become 0.01 into 10 raised to power 20, isn't it? Are you getting?
Yes sir.
हाँ, तो वो जो जो एडिशन करने पे जो वैल्यू आएगा वो नेग्लेक्टेड होगा कंपेयर टू दिस वन. ओके, सो अपने आप नेग्लेक्ट हो जाएगा. Now similarly, if I want to write conductivity of p type material, conductivity of p type. So similarly, in p-type material, we have holes equals to impurity atom, and we have electron equals to Ni square upon Na. Okay. So again, I can use the same formula. Okay, and I can write conductivity of p-type material equals to holes. Okay, p pp e mu p plus np e mu n. Okay, and this is equal to pp is equals to what? Pp is equal to na e mu p plus np is equals to ni square upon na e mu n, and this will be again neglected, so you can write the semiconductivity of p type is equals to na e mu p. Now what happens अगर सिस्टम में, in your system both type of impurities are present, आपका होल भी प्रेजेंट है, ओके, और आपके एक्सेप्टर आयंस भी प्रेजेंट है, एंड डोनर आयंस आल्सो प्रेजेंट, both type of impurity are present. Okay, in that case we have to modify the expression for conductivity. Okay, so let me write now if both are present. क्वेश्चन में देने दोनों दे दिया है, if okay, if both, okay, both the nd and na are present in host material. host material host material का मतलब जिसमें डोप कर रहे हैं, ओके, और सेमीकंडक्टर. तब क्या करेंगे? in that case we have to find effective charge carrier density. Okay, so suppose if my nd is greater than na, okay, then my effective density of charge carriers will be nd minus na. Okay, then you will use the formula for conductivity. The sample will be effectively n type, and you can write the conductivity as nd, this will say n dash, okay, n dash, okay, mu n e mu n, that is equals to nd minus na, okay, e mu n. Okay, you can write the formula this way. You always take difference, और ये इस फॉर्मूले में नहीं है. जब भी दोनों मिक्स होंगे तो जहां जहां आपको एनडी लिखना था वहां आप एनडी माइनस एन लिखोगे, इवन द इन द फॉर्मूला ऑफ फॉर्मुलर पोजीशन, इफ द क्वेश्चंस आर लाइक कम लाइक दैट. ओके, अभी तो आए नहीं एग्जाम में क्वेश्चन ऐसे, पर ऐसे क्वेश्चन आ जाते हैं एग्जाम में वेयर यू हैव एन टाइप दोनों तरह की इंप्योरिटी है. ओके, तो अब आप हमेशा लेंगे इफेक्टिव डेंसिटी, इफेक्टिव चार्ज कैरियर्स लेंगे फॉर्मूले में भी, किसी फॉर्मूले में भी, वेयर यू आर राइटिंग एनडी you will write instead of nd you will write nd minus na, okay, whenever they both are present. Similarly,
So why not addition? Both are
huh?
present. Why we don't add subtraction?
No, we just want effective density, okay, which are more, because there will be recombination, na? Recombination, when electron holes are both are present, the same time recombination also taking more the concentration of electron, more the recombination. Okay, so recombination you have got effective density only nd minus na. Okay,
ऐसा कह सकते हैं कि मतलब जो बाकी बचे हुए न्यूट्रलाइज हो जाएंगे, जो एक्स्ट्रा है बस उनकी वजह से
Yes, yes, exactly. बाकी न्यूट्रलाइज हो जाएंगे
Sir,
इफेक्टिव हमको हाँ
this also we will that mu p will be neglected.
yeah mu p also neglected because we effectively now it will be n type. Okay, so effectively it will be n type, so you take mu n. Similarly, if you are okay na is equals to greater than nd, okay, in that type you sample becomes effectively like a p type, and you can write what na minus nd e mu p. This formula you have to use. Okay, so far this much they have not asked questions. Okay, but in future they can ask.
Sir,
So I
if
will give you
nd
some
equals to na, there will not be any conductivity.
uh, that and this not there will be no connectivity, we cannot say. Okay, if nd minus nd equals to na impurity, but that is a no purpose na. Why do it is theoretical thing na? Theoretical thing you are telling that if you are putting both nd and ne. Okay, so exactly what we are doing whenever we have some system crystal. Okay, either you want to make it n type or other you want to make p type. Okay, but there always some defects will be, some impurity will be there. Suppose even I want to make n type, so my crystal will not be perfect. It may have some p type impurity already present in terms of vacancies or some defects. Okay, so when I put doping with n type, so I will not get the effective density what I'm trying to get. Are you getting my point? Okay, so that's why we are taking this nd minus na. There's no purpose keeping nd minus na equal. If it is equal, so then what? Then you will get only intrinsic connectivity. Okay,
Yes, sir.
so these are the formulas you have to remember. So now let me discuss temperature dependence of conductivity, which is very important. Okay, temperature dependence temperature dependence of extrinsic conductivity. I am explaining with the help of n-type material. Okay, that will be same for p-type material. Now, in order to explain the temperature variation of conductivity, okay, first we'll see the how carrier concentration varies with temperature. Okay, so basically, extrinsic semiconductor has three ranges. Okay, one is low temperature range. The second one is your mid-level temperature range. Mid-level temperature range. Okay. This is also called frozen range, frozen temperature range. Frozen temperature range. Okay, and then one is high temperature, high temperature range, or also you call intrinsic temperature range. Intrinsic temperature range. Okay, so mid-level temperature already we discussed. Okay, there all the impurity atoms are ionized, so your conductivity is basically what constant. Okay, now let me discuss the temperature variation. So first of all, let me discuss what happens to carrier concentration at low temperature. Okay, so carrier concentration, okay, at low temperature. I'm writing for n-type material. N-type material. Okay, carrier concentration. So carrier concentration at low type material is given by 1 upon NC ND. Okay, Don't write N. Okay, so only N. Carrier concentration in N-type material is given by exponential minus EC minus ED upon 2 kBT. Okay. Now ED is what? ED is the donor level, energy of donor level. Okay. Energy level of donor. Okay. Now you can again go back to the flat band diagram of semiconductor. Okay, this is your conduction band and this is your valence band. This is your EC, this is your EV. Okay, and somewhere here you have donor level, isn't it? So, and this is my EC, this is my gap EC. Okay, now all the atoms are present here. Okay, now if you want to ionize, then you need to supply the energy, isn't it? So if you want to supply energy, when you supply this, when this much energy is available, then only they will go from here, electron will go from here to here. In the case of ND, okay, you have ND here. Now this ND will become ionized whenever it gets this much energy. If your energy is lower than this one, okay, then they are here only. Okay, so I'm talking about a frozen temperature which is well below the required temperature, okay, to get this energy. So in this energy range, low temperature range, your expression is given by this one. As I give the energy, okay, all the atoms present here, they'll get ionized. That will come mid temperature range, where I'll get constant carrier concentration. Okay, so this is basically ED is basically equals to your EC minus ED. So first you need to supply this much energy to ionize all the atoms. Okay, so this is your first. This is the low temperature range concentration. Okay, now if I want mid level temperature concentration, mid level temperature. Okay,
Sir,
so what?
at low
Ah,
temperature,
yes.
would they be able to go in the EC? Matlab,
That's why I'm asking. No, slowly, I'm taking range. You're slowly increasing temperature. You are at frozen temperature 10 Kelvin, and then you're going 10 to 20, 30, 40, 60. Okay, and slowly you're reaching to room temperature. So as you are increasing the temperature, slowly they're ionizing. Na? Okay, suppose 1,000 electrons are there. So first 10 go, next 10 go, next 10 go. So slowly they're ionizing. So slowly your conductivity is increasing. And at mid level, that become ND. So one become N become ND. Okay, the conductivity becomes, carrier concentration become constant. So I'm talking first carrier concentration. Okay, dependence. Then we'll talk of, this conductivity. Now carrier concentration is increasing slowly. Okay, this is the second part. Now what is third part? Now if you go very high temperature range, okay, if you go very high
Sir,
temperature range,
at a low temperature, all donor atoms are not there.
now all donor atoms are not ionizing. If 0 degree Kelvin, nothing is there. Okay, it's like insulator. No electrons are there in conduction band.
In conduction band.
Once you increasing temperature, slowly conduction increasing. Okay, so high temperature range, this is called intrinsic range. This is called intrinsic range. So here intrinsic conductivity dominates. Okay, because obvious intrinsic atoms are more. Okay, so now here intrinsic carrier density dominates. Electron can come from valence band to conduction band. So your nature of conductivity now will be like intrinsic conductivity. Okay, so here at high temperature, I can write what N is equal to what? What was the formula for this one? E power Eg upon, okay, Eg upon 2 kBT type of carrier concentration. Okay, what was there? Carrier concentration was, if I take N, okay, that was what? B T power 3 by 2 E power minus Eg upon 2 kBT, isn't it? The formula for intrinsic carrier concentration. Let me check.
Yes, sir.
Just now you have carrier concentration. Okay, you can find now the your conductivity. Okay, so at high temperature, now at high temperature what happen, this this will dominate. Okay, this will dominate, this factor will dominate. So this temperature range will not dominate at high temperature. Okay, so this exponential term will dominate. So if I now plot, okay, if I plot, okay, my
Sir,
carrier concentration, हाँ बोलिए.
how this is possible? In an exponential term, temperature is in denominator, na?
हाँ,
Temperature and
that is also minus na, that is also
how?
minus. Okay, so if you have a temperature, okay, high temperature, then this will be lower. Minus में lower means plus में higher ना नीचे के, so dominant factor will be your exponential. Okay, always if you any plot in graph, in low range your x power dominates, but at higher power your e power x always dominates, isn't it? Okay, suppose you
Sir,
have a
what
using
about
x upon e, you have x upon e minus x. So what will the graph? Initially it will be like this, and this will go down. Okay, so exponential power always dominates. हाँ बोलिए.
sir? What about that donor level concentration and acceptor level concentration?
Yeah, we're talking about it now. Now if I plot the conductivity graph, okay, so I am plotting now 1 by t versus plot. Okay, 1 by t versus plot, and this is your I'm talking about carrier concentration. Okay, so what will happen at high temperature? This is high temperature range, because I'm plotting 1 by t. So this is high temperature, and this is your low temperature. Okay, now if I plot the conductivity graph, this comes like this. Initially it's exponential, in between that is constant, and at low power it is again getting uh, like slope. So slope of this graph is now what? Slope of this graph is now your minus ei upon 2 kt. Okay, ec minus ed. Okay, just now what have you written? ec minus ed, exponential ec minus ed, and this is what? Ec minus ed is what? Your ionization energy. ec minus ed is your ionization energy. So just to correct if I did mistake, so ei is what? Ionization energy. ec minus et is your ionization energy. Okay, so the exponential of ei upon 2 kbt. So this from this slope, okay, you are slowly, this is low temperature, now you're increasing, you are increasing slowly temperature. So when you're increasing temperature, what happens? Your ions, your impurity atoms, they are get ionized. Okay, in this range all the atoms are ionized, so your n becomes now constant, equals to nd for your n type of semiconductor. For p type semiconductor, p becomes equal to na. Okay, now if you go very high temperature range, okay, now what happened? Your intrinsic nature dominates. Now your conductivity become shows a variation like from here to here. Now more intrinsic carrier comes, this level you already reached. Now more electron comes from intrinsic range. So now the variation will be temperature like intrinsic variation. So here the slope of this graph will give you what? Band gap Eg upon 2 kbt. We already seen this one. Okay, so this is the variation of concentration with temperature for extrinsic semiconductor. Okay, now I want to, so this range, okay, this range is called ionization range. Ionization range. Okay, ionization range means here your atoms are getting ionized. That's why this ionization range. Here all the atoms are ionized. That means your material become extrinsic. So this is called extrinsic range. This is called extrinsic range. Okay, because your all the doping what you've done, that become useful now. All the atom become ionized. You're getting useful conductivity here, mid-level temperature, room temperature and above 100 Kelvin. Okay, and you go very high temperature range. What happens? Your material again try to become intrinsic. Of course, conductivity increased, but now so many electrons comes. So what happens? Your n and p tries to become equal. Okay, so this become intrinsic. So this become intrinsic range.
Sir,
Ah,
Sir, we can say that at high temperature, intrinsic and extrinsic semiconductors, they both do the same work.
No, same work they cannot do. Same work means what? Nah, the
I mean,
material become intrinsic, na, high temperature.
yes,
So
yes.
the problem with intrinsic semiconductor is that they not give you conductivity at low temperature, usable temperature, isn't it? So that's why we are doing doping. The purpose of the electron, they also have electron valence band, but they need very high energy. Okay,
So
so
वही
we don't
ना,
get. Huh?
मतलब एट हाई टेम्परेचर अगर वर्क करना है तो हम
हाँ,
इंट्रिंसिक भी तो ले सकते हैं ना
yes, yes, yes,
एक्सट्रिंसिक की
yes,
जगह.
yes, yes, yes. At high temperature, you take only intrinsic. Okay, but at high temperature, how much high that we have to see. Okay, now if suppose if you keep on increasing the temperature, you may reach to melting point of material. Na? Suppose multiplied 2000, you can go up to 1000. Okay, and then that much, how much you're getting here? What it is here it is adding, na? Whatever you given low temperature, that also adds here. Okay, if this is not there, then this will not plus, na? Are you getting my point? This is also there, and then you're further you're giving, so now number keep on increasing, you're getting more. But now this will try to make because ni depends on temperature. As you keep on increasing temperature, okay, you get boliye.
Sir, does this graph show that at a high temperature, extrinsic semiconductor behave as an intrinsic?
behave मतलब conductivity number तो change हो जाएगा, but behavior like a intensity, your Fermi level again will try to come down. As you increase the temperature slowly, when you do doping, your Fermi will go up. If you go with high temperature, your Fermi level again comes down. Okay, so at high temperature again Fermi level comes down. Similarly, if it is p-type material, it will again move towards intrinsic. If you increase the temperature, position Fermi level goes from bottom to again above to twice mid. So Fermi level movement take place. Okay, so this is your carrier concentration. Now what happens to conductivity? Okay, so conductivity has a mobility factor also, and I already told you mobility varies how. At high temperature, your mobility, okay, decreases with temperature as you move t power minus 3 by 2, and at low temperature it is t power, okay, you should make slightly bigger, 3 by 2. Okay, now the graph will be same for both. Now if I plot a graph of conductivity, so what will happen, this graph will be same. Here just you have a bump, and here you go like this. Okay, so this is your conductivity of n type of material. This is the n type of material. Temperature dependence of conductivity. Okay, now let us do some problems. Okay, shall I erase this one?
Yes, sir.
Now here ionization. Okay, this is only first ionization. Are you getting my point? It's not like you can keep on ionizing impurities, because okay, like you have impurity atoms. Okay, they have some they some also have ionization range. Okay, so you are only ionizing first ionization, which is very close to conduction band. Okay, these inner level, they may require more energy than your band gap. Are you getting? So impurity atoms also you are only ionizing first ionization. So whenever you increase your uh, impurity is not getting ionized again and again. It's not like for like first and second ionization, third ionization. Okay, that depends on the energy levels of impurity. So they second ionization may require more energy than your band gap. It may have 4, 5, 6 electron volt. Okay, so only first ionization is taking place. We're considering it. So this is your temperature variation. Okay, so a question came in exam. In an n-type silicon sample, the Fermi level is 0.3 electron below the conduction band edge. Okay, so Fermi level EC is 0.3 electron volt below, okay, the conduction band edge. The conduction band edge. Okay, find the electron and hole concentration in the sample. Find the n-type sample is there. Okay, so find the concentration of hole and concentration of holes. Okay, concentration of holes in the sample. How do you do? How do you calculate?
Sir,
कैसे कर
0.3 electron volt
हाँ
below क्या है?
0.3 below the conduction band edge. Okay, so you have been given a sample. Okay, whose EC is like this, and below EC you have Fermi level. Okay, your EFN is given
EC minus EF is
0.3 electron volts. Below है, so it is minus. Okay, yes. EC minus EF, basically EC minus EF is given. EC minus EFN is given equal to 0.3 electron volt.
EC minus EFN is KBT ln NC by ND. इससे कर सकते
उससे भी कर सकते हो. And see, they are given you intrinsic carrier concentration also. They have given you silicon. They have given you band gap also. 1.1 electron volt band gap, and then he given you Ni also, and Ni value they have given you 1.5. Okay, this is the exact value. 1.5 10 raised to power 10 per centimeter cube. Or
temperature.
so how can we calculate? Okay, so now see, if I want to calculate this one, I want ND. I want N equals to ND. Na? I want ND, and I want, if I ND known, I can find the number of by Ni square upon ND. Okay, so first I need to calculate ND. So relation between ND and Fermi level. Okay, so what is the relation between ND and Fermi level? If you want position of Fermi level Fn, that is equals to EC minus KBT ln ND upon Ni. Okay, EFI, here it is EFI plus either use this formula or you can use second formula. Second formula is what? EC minus KBT ln, what is the formula? NC by ND. You have two formulas, but you cannot use, can you use this formula here? You gap, this difference is given, but you don't know NC, na? For NC either you have to calculate NC by formula if the temperature range is given. Okay, so if temperature range is not given, you cannot find this with this formula. You don't know NC. Okay, so I can use this formula. Now in order to use this formula, I want EFI. Okay, for that they have given you band gap. So this is your EC, this is your EFN, and you have here somewhere EFI, which is half of EG by 2, isn't it? This is your EV. So they have given you gaps. Okay, now you can use this gap, okay, to find EFI. This is EFI. Okay, so if I want this gap, I want EFN minus EFI. You want EFN minus EFI. So for that, what I can do? I can take this gap and minus this gap. Okay, so this gap is what? EC minus EFI minus, what should I write? Minus, yeah, I want this gap. So I can take this gap, EC minus EFI minus this gap, EC minus EFN, EC minus EFN. Okay, now you this gap already you know what is EFN minus EFI. This gap already you know, EG by 2. EG they have given you, this is EG by 2. Okay, and this gap already they given you 0.3 electron volt. 0.3. So you can solve this one. You can find EFN minus EFI. Okay, Ni is given, KBT is given, T take room temperature, and ND you can calculate ND. Once you know the ND, you can find the this PN. Okay, solve it and tell me the formula. Tell me the values. Take T equal to 300 Kelvin. Okay, take T equals to 300 Kelvin. So this is the homework. You have to send me the solution of this question. And calculating NC is difficult, right? Because you don't, they have not given you that what is the effective mass of electron. Okay, even if it is given, then you can find, you can use SC also. With this value also you can find NC, that they'll come close. So this question is clear or not? Lakshmi, Sri Lakshmi,
Yes, sir.
question clear?
Yes, sir.
Okay, please send me solve and send me the Vinita. Okay, others also please try and send a solution. I'm stopping here.
सर
हाँ,
एक बार बताओगे आगे कैसे प्रोसीड करना है?
अरे आगे तो बता तो दिया, जब ये निकल गया, गैप निकल गया,
हाँ
ये गैप, ये दोनों गैप निकल गया, तो ये पता ही NI आपको पता ही क्वेश्चन में दे रखा है. ओके, ND निकालना है, इस फॉर्मूले से ND निकल जाएगा. अगर ND निकल गया आपका, ND निकल गया तो ये आपका ये भी निकल जाएगा, होल्स भी निकल जाएगा. NI ऑलरेडी क्वेश्चन में दे रखा है, NI स्क्वायर बाय ND. ये दोनों तो पूछा है. फाइन.
ओके सर.
Okay, thank you. I'm stopping here.
Thank you, sir.
Thank you.
थैंक यू सर.
Thank you.